Welcome to the afternoon session, and our first speaker is Richard Kueng, who will talk about faster quantum and classical SDP approximations for quadratic binary optimization.
Yes.
Take it away.
Thank you very much. I'm Richard Kueng. You were probably expecting Fernando Brandao, but he couldn't make it, and so instead I'm replacing him, but I'm talking about a joint project that we did together at Caltech. So Fernando, myself, and Daniel Stelk-Franke, who is in Copenhagen. And this is a very complicated title, but we were all very excited by the recent developments regarding quantum speedups for optimization problems that were arguably started by Fernando Brandao and Christa Svor in 2017. And this was all very surprising to us. But unfortunately, the entire approach depends on problem-specific parameters, and these parameters explode for some of the most important application of semi-definite programming. So there was a gaping hole in the theory, and we tried to fill that. And SDP approximations for binary quadratic optimization are exactly the kind of problems that the original approaches couldn't address. And I will try to point out why, and I will try to give a rather conceptual talk about how we managed to overcome this. Okay, so here's a brief outline of my talk. I want to give a quick motivation, very broadly, and then focus on the problem we want to consider, SDP relaxations of binary quadratic problems. And then I want to actually take some time to develop a quantum-inspired meta-algorithm. It's actually very similar to mirror descent, for those of you who know, that is able to address the specific structure associated with these kinds of problems that made it hard to tackle with the existing SDP solvers. And then I will do a quick runtime analysis, because this meta-algorithm can be implemented either on a fully classical device, but if we had access to a quantum computer or new ideas on how to simulate quantum computers efficiently, this can be further boosted. And at least on paper, the results I will show regarding runtime are actually competitive. And then I want to do a quick summary and close this. So let's start with the motivation. As I already said, I find this very exciting, but quantum algorithms for optimization tasks is a very promising, rather new idea, I would say, and with a broad scope of possible applications. And today I want to mainly focus on speedups for semi-definite or convex optimization problems, and there we know that also classical solvers are efficient in theory. Convex optimization problems are not difficult from a TCS point of view. But the problem is, if you actually want to run them, they get slow very, very quickly, and storage is a problem. So what we are hunting for here are not these amazing exponential speedups that some quantum algorithms promise, but more milder speedups, but for arguably a very broad and useful class of problems. So the stakes are a bit lower in this talk. We want to do polynomial speedups only, but at least have a broad range of applicability. Okay, so that's the main idea. And an important example, as I pointed out, what I want to focus on is semi-definite programming. But one of the tricks that we will use is we will actually don't use the semi-definite programming structure, but embed it in a more general convex optimization problem. And as I also already said, existing quantum algorithms, at least the one by Brandao and Svor, who were later improved by Andras and his gang from the Netherlands, don't always yield improvements, at least don't always yield improvements. So they depend on problem-specific parameters, and you have to check that first. And it can happen, and in fact, sometimes it happens that you don't see a speed up. And so we want to focus on this. And the most important open challenge for us that was really vexing are relaxations of binary quadratic problems. They are very, very popular in the computer science literature. Some important advances like matrix multiplicative weights were developed specifically to address these problems. And this is arguably a battlefield where the classical competition is particularly strong. And so we wanted to address that. And we found some mild improvements, but again, I want to emphasize it's rather mild compared to other branches. And our ideas to tackle this problem and to overcome shortcomings of existing SDP solvers is the first thing we have to do, and I will emphasize that later, is we have to bundle many linear constraints together. So typically you phrase an SDP as a problem with linear constraints, a linear objective function, and a PSD constraint. But nothing in principle stops you from bundling several linear constraints together and view it as a more general convex optimization problem. And we will have to do that to overcome the shortcomings. And the second important idea is that we developed a primal-only classical algorithm. So the original quantum SDP solvers were motivated by matrix multiplicative weight algorithms developed by Aurora and Kale, and they kind of jump back and forth from primal and dual solutions in order to arrive at an optimum. And this kind of introduces a dependence on the size of the problem. And this can actually be overcome by just looking at a primal-only solution. And this is very similar to mirror descent. And finally, as it I think now a mainstay, is we kind of embed quantum simulation, like Gibbs sampling, as a fast subroutine that could in principle speed up the classical procedure further. So we are building a pretty fast classical algorithm that has a bottleneck, mainly computing matrix exponentials, and then we are going to use potential quantum devices to speed up the subroutine of computing matrix exponentials. So that's the high-level idea that allowed us to address these kind of problem classes with the original ideas by Fernando Brandao and Chris Tesfaye. Okay, it's about time to introduce the problem, I think. And binary quadratic optimization are problems of the following form. We have an n-dimensional vector, but with binary constraints. So it can only be plus or minus 1. And then we want to optimize, say maximize a quadratic function in these binary vectors. It's a very general problem. It appears, it has a lot of applications, and it's very nasty. It looks like there's integer constraints, and a naive approach would require exponentially many test cases to find the optimal solution. Important examples include, and that should already scare you, max cut and cut norm. Important graph theoretical problems. In data analysis, community detection can often be phrased in this way. And something that is very near and dear to me, it turns out that if you're interested in rigorous structured matrix factorizations, then these can often be formulated as problems of this form. And so they also appear there. And if you are a true physicist by heart, then just think about Ising models and spin glasses. Similar problems, classical Ising models. So this is a binary quadratic optimization problem, and it should shock nobody that this is hard in general. And so an obvious way to tackle hard problems is to relax it to something that is easy, at least in theory, and that's what the SDP relaxation does. So let me rewrite this problem again. I kind of reformulate it a bit because I can consider each x, I can rewrite the quadratic function as a linear function in the outer product. And the outer product is always positive semi-definite. I can replace it by a matrix X. And because the original vector is diagonal, you can quickly check that this outer product only has plus ones on the diagonal. And so equivalently, by replacing this XX adjoint by matrix X, this problem is equivalent to the following problem, where I also have to introduce an additional rank constraint, because here I'm only optimizing over outer product. And the SDP relaxation is pretty simple. It just says, this is a nice constraint, this is a nice constraint, this is SDP constraint. This is very nasty. Let's just not do that. Just erase it. And then you arrive at an SDP relaxation of the problem. And this is the problem class of semi-definite programs that we want to address today. And this convex relaxation is kind of nice. The objective function is linear. And the constraint set is an intersection of two convex sets, where one of them is a convex cone, just a cone of positive semi-definite matrices. And the other one is the set of all matrices whose diagonal entries are nailed down to be ones. And there's two ways of viewing that. You can either view that as an affine constraint, it's a collection of linear constraints, as a single affine constraint. Or if you actually want to go to traditional SDP formulations, you would divide that up into n different linear constraints, where each of the constraints would tell you the first diagonal entry has to be 1, second diagonal entry has to be 1, third diagonal entry has to be 1. And this turns out to actually be the problem for the existing solutions, because this constraint immediately tells you that every feasible matrix here has to have a very large trace. Depends on the dimension. And if you do primal dual approaches, then they usually depend on the size of the problem, and the size of the have an additional dependence on the size of the problem, and this is very large here. And so if you just take the existing results by Brandao and Swaw, for instance, they depend on a parameter that is kind of related to this. And it is an extra dependence that is a very large polynomial. And so if you insert that, all your speedups are gone. Like your runtime immediately becomes much, much worse than a standard interior point method. And so somehow we have to overcome this problem that the size of these particular combinatorial optimization relaxations is unusually large for standard matrix multiplicative weight approaches. Okay, so I've written again the fundamental problem of this talk. SDP relaxations of binary quadratic optimization, linear optimization function, these diagonal constraints, affine constraints, and I've also included, it's not necessary, but if every diagonal entry has to be 1, the trace has to be n, and the matrix has to be positive semi-definite. Now I want to get this a bit closer to quantum mechanics world, and so I rescale the problem by kind of enforcing each of the diagonal. I just rescale the problem such that each of the diagonal entries has to be 1 over the dimension, and this has an effect on the trace, namely the trace is 1. And now this second constraint that I call by calligraphic S is just a constraint that we are actually optimizing over density operators, over density matrices. And then we're optimizing a linear function subject to an affine constraint that I call C1. So far, not much interesting has happened. I've rescaled the problem. I have to keep track of that, because when we look at approximations, I have to remember. But so far, not a big deal. I just want the X to look more like a quantum state, to use quantum intuition. And well, this is the problem we want to tackle. Let me try to introduce our meta algorithm for that. And it's kind of a 3-phase optimization algorithm. And the phase 1 is very similar to matrix multiplicative weight and what Aurora and Kale did. We start with an optimization problem, but binary search allows you to reduce this optimization problem to a sequence of feasibility problems. And that turns out to help. So we kind of start with an optimization problem, replace it by a sequence of feasibility problems, and then we are left with solving feasibility problems. And for that, we develop a quantum-inspired meta algorithm. It's very similar to mirror descent, for those of you who know. And then in phase 3, there's like a potential quantum boost, or let's be more honest, call it a smart idea boost. There's one bottleneck in this meta algorithm, and when you can make progress there, then the runtime improves considerably. Quantum computers are one possibility for that. And the inspiration is, again, matrix multiplicative weights, but we never considered a dual. So it's actually more similar to a mirror descent approach. And just very quickly, this is a standard trick in optimization theory. The objective function in our problem is a linear function, and it is also bounded. So the values are always in a unit interval between -1 and 1. And so you can, instead of optimizing your objective function directly, you can choose a parameter in a possible range and ask, is there a feasible solution to my problem that kind of whose function objective value is smaller or equal than lambda? So kind of I replace an optimization with a sequence of questions, and if I'm able to answer this question, I can just scan through the interval of all possible solutions and effectively nail down the optimal value. So binary search allows me to do that. And the overhead is very mild. If I'm interested in epsilon accuracy, and because we're in a unit interval, because I rescaled, we only need to answer tilde O, so like ignoring logarithmic factors, we only need to answer a couple of order 1 questions about the feasibility of a potential solution. This is a standard trick, but it's actually important because for us in this framework, solving feasibility problems is easier than optimization. And now we have a feasibility problem. So we have an additional parameter lambda. That's the question. Does an objective, a feasible point exist whose objective function is smaller or equal than lambda? So we get a new constraint. And these are just the original feasibility constraints. Diagonal has to be equal to 1, rescaled, and we are optimizing over density matrices. So this is the problem we actually want to address with our meta algorithm. And we just have to find a matrix, and the matrix has to be in the intersection of 3 nice convex sets. The new constraint is a half space, just a linear function. It has to be smaller than a certain value. The second constraint is an affine subspace of all matrices whose diagonal is 1, whose diagonal entries are constant. And the third constraint, it's the most interesting one, is that the matrix also has to be a density operator.
You also just like trace X equals 1, you can absorb it into the affine space.
Pardon?
You can absorb trace.
Yes, exactly. I agree. I agree. This is a superfluous constraint. I agree. yeah, it's going to be important if you want to relax the constraints a bit, because maybe you want to have trace exactly equal to 1, while you might be happy with some small inaccuracies there. But you're right. In theory, I just wrote one constraint twice. Very good. OK, I called this a quantum-inspired change of variables, but it's really just the mirror descent trick in disguise. This is a nice constraint. This is a nice constraint. This constraint is a bit scary. And when I was a chemistry undergrad, the only trick I ever learned to deal with scary problems is to do a change of variables that gets rid of it. And kind of, we also did that here. We can write every positive semi-definite matrix as a matrix exponential. And matrix exponentials are automatically positive semi-definite. And if I want to nail down the trace constraint as well, I have to divide by the trace. So kind of this seems like a hack, but it is at least kind of like a quantum-inspired, yes, change of variables that makes the last constraint trivial. It will induce new difficulties, but at least I don't have to write down the PSD constraint explicitly. And exactly, this change of variables ensures that my matrix is automatically positive semi-definite, but we have to now reason about nonlinear functions in the new variable, namely the Hamiltonian or the matrix exponential h. And so we have to find a Hamiltonian, a matrix exponential, subject to the associated matrix exponential obeys the linear constraint and the diagonal constraint. OK? And Hamiltonian Updates, the meta-algorithm, just writes down an iterative heuristics that kind of does that. That tries to find a matrix exponential, a Hamiltonian, an energy function associated with a Gibbs state that obeys these two feasibility constraints. And the algorithm is really simple. We just start with the zero matrix, or in physics language with infinite temperature as a starting point. And then we compute the matrix exponential, and we check if it meets these two constraints. We're looking for a feasibility problem, so if it does, we're done. We found a feasible solution. And if the constraints are violated, we kind of update the exponent in order to penalize the directions where it went wrong. So kind of if it violated the second constraint, we somehow do something to the matrix exponential, add something that shrinks the corresponding directions. And because it's a x minus something, we are just adding something, and x minus something becomes smaller. So that's the heuristics idea. Here's maybe a couple of pictures to illustrate that. Here in this circle, this denotes the set of all positive semi-definite matrices. Our change of variables to care of that. And suppose we are the current iteration rho, and we are looking for a point in the intersection of an kind of a non-trivial convex set, part of a diamond here, and a half space. And what the algorithm proposes is, because all the sets are convex, this point is in one of the convex sets, but not the other one. And so there exists a separating hyperplane that separates the two. And then I just add that in the exponent. And heuristically, that should push me in this direction. And then I just keep going. Still not there. Find another separating hyperplane, pushes me down there. And this should converge. And of course it does. That's the magic of mirror descent.
Mirror descent typically might get outside the feasible setting of the project.
Yes.
You need to do that here as well?
No. Because kind of like we don't have kind of like very good. Kind of, we don't do that. We don't do the projection step. We just care that we are always in the space of positive semi-definite matrices, and we are automatically with this construction. And kind of the way we solve this problem is that we will relax the problem and we'll be happy with finding approximately feasible solutions. And then you don't have to project.
And just quickly a follow-up to this.
Yes.
What's the associated Bregman divergence for this mirror descent?
I'm going to say that. Very good. Exactly. Mirror descent magic, this heuristics actually works. And the number of steps it needs is only logarithmic in the number of dimensions. This is why this approach is powerful, at least in theory. And the proof is actually quantum-inspired, also the original proof. And it's very important that we started with the infinite temperature state, that our first iteration was 0. Because then the associated starting state is the maximally mixed state. And we can try to quantify distance in relative entropy. That's the Bregman divergence. And we know that this starting state is special because if a feasible point exists, then the relative entropy distance is at most log n, just a fundamental feature of relative entropy as a distance measure. And then the way how you prove this result is to make sure that at each iteration where we penalize infeasible directions, we get closer in relative entropy. And this is something you can do using quantum tricks. And now we have a certain budget, and then we either have to converge after t steps, like this tells us how big our budget is, or we will get a relation that implies that the relative entropy is negative. And we know that this can never happen. And this is actually a very straightforward half-a-page proof that this procedure actually works after only logarithmically many steps, and the log n comes from this powerful relation of the relative entropy. And to answer your question, the potential function is the von Neumann entropy, the associated Brakmann divergence is the relative entropy, and this is what we use. Okay? So Hamiltonian Updates, this meta-algorithm, solves the feasibility problem in only log n many steps. But the individual steps can be expensive. There's 3 of them. We first have to compute a matrix exponential, and then we have to check the relatively simple convex constraints. One of them is a linear constraint, and the other one is checking the diagonal. And if any of them is violated, we have to report a hyperplane, a separating hyperplane, but this turns out to be easy. You're all experts. Usually I ask which one is the expensive one, but it's, of course, matrix exponentiation. This is the bottleneck. And if you just do a naive runtime analysis, you get a naive total cost that scales like the 4th power in the dimension times the sparsity, and this is really not that impressive. However, the proof here turns out to be surprisingly robust. You can kind of carry out the same argument even if you don't implement each of the steps exactly, just geometrically robust. And you can actually classically exploit that by just computing matrix exponentials dirtily. Rather than computing the full matrix exponential, you do a Taylor expansion and you cut it off after only logarithmically many terms. And it turns out that this is a dirty solution, but it's good enough to drive the algorithm. And if you do that, you can compute your matrix exponentials quicker, and you actually get suddenly something that looks a bit impressive on the classical side already. With this trick, the runtime is approximately n squared times the sparsity of the problem. But the caveat is that we only solve the feasibility problem up to some certain accuracy. But this actually improved about the best general existing algorithm, which had a dimension scaling of 2.5. But because we only solve it approximately, you have to be a bit careful about the approximation errors. And it turns out that for generic instances or for dense instances, the error scaling in this theorem is better. But when you have very, very sparse problems, then the existing algorithm has a better accuracy. And one thing that I have to point out, and that makes me very, very sad, is max cut, the most important problem of this kind, unfortunately doesn't fall into this speed up category, because our algorithm still requires this time. But max cut is based on a graph Laplacian matrix, and this is very rich structure, and so you can just sparsify. This is also something the Amsterdam gang pointed out. But in principle, if you want to solve max cut approximately, you can just directly sparsify and then use matrix multiplicative weights. And this turns out to actually be superior to what we have here. Such is life. That's OK. And now, very, very quickly, the classical bottleneck is compute these matrix exponentials. Even if you want to do it dirtily, it's still expensive. And it shouldn't come as a surprise that a quantum device could potentially speed that up, because we are really looking for Gibbs states. And so the idea is never compute the matrix exponential explicitly, have a quantum computer, prepare it, but then you have to do some sampling in order to estimate your feasibility constraints. But the extra cost of sampling is overtaken by the cost savings by doing this on a quantum computer. And by this, we actually get even better theoretical runtimes. This is the classic, the quantum boost that I mentioned. And this problem actually is the first quantum speedup, at least when we wrote the paper, for these combinatorial SDP relaxations. And it improves our classical improvement, which improved the best existing results, at least for certain problem instances. An important design feature that made this possible is that the Hamiltonian is designed to be very structured. So I think this should also help if you want to get better classical algorithms for computing matrix exponentials, but it also drives the quantum speed up. And with that, I'm done. We kind of adapted mirror descent to address the problem of SDP relaxations of binary quadratic optimization problems. And this allowed us to improve runtimes for these problems in theory. And again, the main insight we had is to bundle convex constraints together into seemingly more complicated single constraints, convex constraints, and then use the mirror descent framework that only requires primal problems to get something that is actually competitive. And yeah, there's a lot of possible future directions, and we already saw kind of in follow-up work that this meta algorithm can be adapted to other interesting convex optimization problems like state tomography. Thanks.
Any questions?
Can you just go to the previous slides?
Yes.
Can you be a little more precise on the last, no, just the one before the last one.
Yes. Sorry. Yes.
Yes. Can you tell us what is the epsilon dependence on these three radicals at the end?
Yeah, thank you. This is a very good point. It's embarrassing.
In all three or in half of them?
Actually, in all three, but it gets progressively worse. I think like our classical runtime with the hack of the Taylor series has a 1/epsilon⁶. And then we became so embarrassed that for the quantum runtime, I think we didn't track it properly, but it might be 1/16 or order 16. So yeah, there's still a lot of room for improvement, and we are aware of that. But thanks. Important caveat.
Sorry, another question. So in the classical setting, if you look at the exports algorithm,
Yes.
so there the mirror descent is equivalent to multiplicative weights.
Yes.
Right. So here you're gaining something by moving to the mirror descent. There you don't get any algorithmic improvement. It's just a reinterpretation. So what is it that makes the mirror
I think maybe I wasn't precise enough. I think matrix multiplicative weights fails if you really consider this problem as a SDP with n different linear constraints. This is the challenging part. We actually didn't do the full analysis for what matrix multiplicative weights would do with the general constraint. But kind of we just simply went to the general constraint, and it was very important to kind of get the accuracy in trace distance there, and then a mirror descent was good enough.
More questions? Maybe I have a question. Do you have some indication that this is somehow sort of what is the optimal bound for these problems?
I don't know them by heart right now.
Could you go down to linear or something?
That is a very good question. I actually haven't thought about that.
There's one more question.
Do you have any intuition about the relationship between your truncation and the classical approximation case? Your truncation
Yes.
of the transition
Yes.
and the resulting error?
The resulting error scales, I think, like with I think we have to include a polynomial scaling in the number of Trotter steps that we incur to get epsilon accuracy. So this is partly responsible for the large epsilons that we get. But this was also like just a naive hack. I'm sure there's like smarter techniques to approximate matrix exponentials more efficiently. But certainly part of the bad scaling in the accuracy comes from this step.
Any last question?
I was wondering, like, how do you get the square root of the sparsity? Is it some fancy Hamiltonian simulation
Yes.
result, like Kueng?
It's the low result from 2019. I would call that fancy, yes.
Okay, thanks for the wonderful